Okay, so good morning, everyone. My name is Shadi Fataya. I'm the chair of this PhD defense today by Nematulloev. He is in the program of chemistry. And today with me, we have Professor Omar Mohammed. We have Professor Luigi Cavallo online. And as an external committee member, we have Professor Ishad Hussain, also online, and the supervisor of Said Osman Bakr. So Said, you have 45 minutes, up to 45 minutes. When it's 5 minutes before, I will just let you know. The title of your defense is Atomically Precise Copper Nanocluster, Synthesis, Motives, and Applications. The floor is all yours.
Thank you for kind introduction. Good morning, everyone. I hope you enjoyed your weekend. It's my pleasure to welcome you all to my PhD defense about atomically precise copper nanoclusters, their synthesis, motifs, and applications. To begin with, I will give you a brief introduction about nanoclusters field, followed by objectives of my work. All my research divided into 3 parts. The first part would be about aggregation-induced emission in copper nanoclusters, the second part about defective copper nanoclusters, and the third part of my work dedicated on transmission electron microscopy investigation of nanocrystals. I will summarize by key conclusion. So let's go. Do you know that 2 nanoparticles are not the same? There is always size distribution. This size distribution, if we zoom in into nanoscale, can be very big. It can be hundreds of atom difference. Therefore, controlling nanoparticles with atomic precision can open up the doors for fundamental studies as well as applications. Here is where nanoclusters come into play. Nanoclusters are very small nanoparticles, size 1 to 3 nanometers with precise structure and magic number of atoms. Nanoclusters are materials which is bridging the gap between molecular chemistry and nanocrystal chemistry. Let me explain you. Nanoclusters are similar to molecules in a sense that they have precise structure and formula. And from the other hand, they are similar to nanocrystals because they have core shell structure. They have many, many advantages. And among them, I would like to highlight that when we have a precise structure on nanoparticle, we can correlate the structure with property, which is very important. In the past, gold and silver nanoclusters have been studied a lot, and they found application in various fields like catalysis, sensing, electronic, and etc. However, these 2 metals are quite expensive, which restricts their possible applications. There is a growing demand on other metal-based nanoclusters. Here, copper comes into play, and there are many, many obvious reasons. Firstly, copper is widely used in catalytic application in sensing and etc., wider than silver and gold. Also, copper is more abundant metal, which make it very cheap. It's like in 2 orders of magnitude cheaper than the gold, for example. It's also biocompatible, and if we look into periodic table, we see that copper is in the same group as gold and silver, which means that they have similar electronic configuration. So why there was no investigation of copper nanoclusters? People tried, however, there were 3 main challenges. The first one is that copper is very highly reactive metal in comparison with gold and silver. It's easy to oxidize, and it has a tendency of aggregation. Copper nanoclusters field growing fast. I remember when I started my PhD, I could count the number of copper clusters with precise structure with my hand. However, by the end of my PhD, now I know that I lost a count how many of them is published. And now the bar is raised, and it's not enough just to crystallize structure and publish them. We need to do more investigation and find an application for it. Addressing those challenges, the objective of my work would be to develop copper nanoclusters with specific catalytic and optical properties, and to investigate their structure-property correlation, using their single crystal as a platform. and to understand the role of structural defects in catalytic and optical properties of copper nanoclusters, and to implementation of TEM to unreveal the growth mechanism, structure, and morphology of nanocrystal. These beautiful structures have been synthesized and published from our group, and I was lucky to be part of all of these projects. However, today I would be focusing on the project which I took a lead, and it would be about copper 15, copper 28, and copper 29. So if we talk about making nanoclusters, there are in general two approaches, top-down approach. When you start from bulk and reduce the size to nano, or there is bottom-up when you start from molecules and atoms and you build up to nano. Specifically for copper nanoclusters, we use bottom-up approach. There are two ways of doing it. Direct synthesis, when we use copper precursors and ligands and reduce them. Or indirect, when we use an existing copper nanocluster, small nanoclusters can be, and we reduce it again to make it big. Or we do ligand exchange in order to get another nanocluster which we want. However, it's not as easy as it sounds because there are many parameters to control. For example, type of ligands we use, type of reducing agent, ligands ratio, temperature, solvent, reaction time, and etc. And there is no general method to synthesize in copper nanoclusters. All of them has a specific parameter which corresponds to it. Only synthesizing copper nanocluster is not enough because we want to know the structure, details of the structure. That's why we need to crystallize them and get a single crystal of them. For nanoclusters in general, we use anti-solvent method of crystallization, and we do it in 3 different ways. By mixing anti-solvent with a solution of nanocluster, or by layering it, or vapor-assisted crystallization. They have similar origin of working. However, the difference, I would say, that the diffusion rate of anti-solvent to the solution. By using this approach, we crystallize those clusters, and the time of crystallization vary from 1 day to 1 month, actually. And it depends on copper nanocluster, what kind of copper nanocluster we are crystallizing. To characterize this material, first and foremost, we use single crystal XRD because we want to unreveal the structure. However, for single crystal XRD, we use a solid material. In order to prove that our material is the same in solution, we use electrospray ionization mass spectroscopy. Mass spectroscopy also gives us a charge state of copper nanoclusters. For optical properties, we use UV spectrometer. Also, another important point in copper nanoclusters are the charge state of copper inside copper nanoclusters. In order to find out the charge state, we use X-ray photoelectron spectroscopy. Also, if we have hydrogen inside the molecule, we should use NMR because by using single crystal XRD, we cannot determine the hydrogen. And also, NMR can be used to understand the ligand environment of the nanocluster. So this was a brief introduction about nanoclusters. So let's move to the first part of my work, which is about aggregation-induced emission in copper nanoclusters. In each part, I would like to give a brief introduction and then go to the work. If you remember in the beginning, I said that aggregation is a problem. However, if we use it in a correct way, it can become an advantage. In general, there is a phenomenon called aggregation-induced emission, which is a photophysical phenomenon when non-emissive or weakly emissive material become highly emissive upon aggregation. This kind of materials has been already used in displays, bioimaging, and waveguiding. The interesting thing about this, if we go to a timeline of this material, that it was discovered recently. Before 2001, there was a understanding that aggregation quenches the emission. And first time in 2001, the Tang's group observed this phenomena in organic molecules. That's why this material was used a lot in organic LED. Since then, there has been a lot of work on organic materials, And only in 2012, there was a publication about gold nanoclusters that when they observed this phenomenon. Since then, there was some work on copper nanoclusters when they also observed this phenomenon. However, in these three works, they couldn't crystallize the material, and they didn't give structural details and how it is affecting or originating this phenomenon. And in 2021, by using common thiolate ligands and phosphine ligands, we, in our group, synthesized and crystallized new copper nanoclusters, which has 15 copper of atom, and which has also aggregation-induced emission phenomena. Let's talk about the synthesis of copper 15. It is one-pot synthesis method. We dissolve copper complex together with ligands in the mixture of acetonitrile and chloroform, and we reduce them by using sodium borohydride. After the reaction, we remove the solution part and we dissolve the residue in chloroform in order to crystallize them. As an anti-solvent, we used hexane. And after 2 days, we got the crystals which showed highly emissive. However, these crystals were not emissive in solution, which means that there is a phenomena which is aggregation-induced emission. Also, we did PL lifetime, shows that radiative recombination in this material is phosphorescence because the radiative lifetime is in the range of hundreds of nanoseconds. Let's talk about structure of this material. Structure is unique, it's new, there was no such structure previously published, and this structure also was a chiral. Overall structure had a 3 fan blades type of structure, which has 2 enantiomers, which we call clockwise and anti-clockwise enantiomers. However, the interesting part of the structure is a ligand, because we observed that there are weak CH pi and pi interactions between the benzene ligands of the nanocluster. What they are doing, they are actually restricting vibrational and rotational movement of the cluster, which is also minimizing the non-radiative recombination. That's why we are having a high luminescence in the solid state rather than in solution. Also, as I said, the charge of copper is very important because it will determine the possible application of it. And then we did XPS to find out what is the charge. Specifically in copper 15, all coppers inside the material was copper +1, which we found out from copper element spectrum. To sum up, I would like to highlight that we synthesized novel copper nanocluster called copper 15 by using an available ligand, and we performed a characterization of it. Our findings show that the copper 15 exhibit aggregation-induced emission, and it has much stronger photoluminescence in crystalline state than in solution. And also, important part of this work was deep structural investigation, which showed that CH pi and pi weak bondings play a crucial role in aggregation-induced emission phenomena. This was the first part of my talk. Now I would like to move to the second. Okay, now I will be talking about defective nanocluster. In general, defect is something negative. It's a shortcoming, it's an imperfection or lack. However, if we can use it in a direct and correct way, it can become an advantage. In general, defect in nanoparticles are important, and they tailor the catalytic properties, optical properties, etc. Here, nanoclusters are the perfect platform to study defects because we know everything about it. We know the structure, and we can correlate the structure to the properties and application. I would like to start my talk about the first defective copper nanocluster, which was published from our group. We call it copper 36. If we look into this structure, half-cube structure, we see that 2 atoms, the green, are missing from the surface, which we call surface vacancy. These vacancies are causing structural distortion, as well as there is an electronic state change. However, in this project, we couldn't synthesize and crystallize the non-defective version of copper 36, which is copper 38. Why we need it? Because we want to compare them directly. Copper 36, which is defective, and copper 38, which is non-defective. We were lucky to get clusters which are non-defect and defective version. So we call it copper 28 and copper 29. As we can see from structure, we are missing one atom of copper on one of the vertex of this tetrahedral structure. We'll come to the structure later. The synthesis approach is very similar to copper 15, except the ligand and conditions like time and differing solvents. Without going to the details, let's go to the structure itself. These two structures has a lot in common. They share same copper 13 anti-cuboctahedron core, and they have similar staple motifs. However, as I said, there is a distortion on the site of vacancy. We can see it more clearly in this picture. As you can see, vacancy causing the distortion in that site at the same time that it's lowering the symmetry. As we can see, copper 29 has a C3 symmetry, and in case of copper 28, the symmetry is much lower. And this defect is not causing only structural change, it's causing also electronic structure change. So DFT calculations show that in case of defective copper 28, we have HOMO levels all located in a defective site, which means that this site is active. It can be used as an active site for catalytic. In case of copper 29, they are distributed equally. And in the beginning, I mentioned that we need to prove that our material is the same in solution. So here we were puzzled on the mass spectroscopy of this material. We have copper 28 in solid when we do single crystal XRD, but when we dissolve it, it becomes copper 29. So how it's possible? Firstly, I want to mention that when we found out copper 28 formula, we found out that it is natural cluster. So there is no charge. As we know, in mass spectroscopy, we cannot see any natural species. So what's happening is one copper of atom is attaching to copper 28 to make it copper 29, which we can see on the mass spectroscopy. Also, we observed an interesting thing regarding the ligand, 3-phenylphosphine. Initially, there is 3 ligands in copper 28. However, in the spectrum, we see 4. And this is what's happening, and this is the proposed, our hypothesis that why it's happening. As we know, there is a defective site in copper 28. And when we are in solution, especially when we are doing mass spectroscopy, there is high temperature, as well as we are applying some voltages. And there is this gas phase rearrangement, which when the copper with 3-phenylphosphine is attaching to the defective site. It makes sense because it's making it highly symmetry material. And this is our hypothesis. The next part of my talk would be about catalytic application of this defective material. In general, catalyst is a material which speeds up a chemical reaction without itself being consumed. Nanoclusters in general, they are not new in the catalysis field. They were used in different reactions, all of them like gold, silver, copper. However, here we have an advantage of having a defect. So with collaboration with Professor Magnus' group, with Dr. Saga, we tried our defective material on photo-induced CC Sonogashira coupling. Conventional catalyst for this reaction is palladium together with copper complexes or copper in different states. However, the problem here is the formation of homocoupling product, which is difficult to separate from main product. When we used our material as a catalyst, we found out that there is no homocoupling product. This is a huge advancement. And also we found out that the reaction yield is quite high. So we tried to find, different scopes. We tried different aryl iodide scope and different alkene scope. And in all cases, we found out that the yield of reaction is high. And also Importantly, there is no homocoupling byproduct. The mechanism which we proposed is single electron transfer. When we excite our material, our cluster, one electron is transferring to aryl iodide, making it to dissociate to aryl radicals. Aryl radical was detected with gas chromatography, and then aryl radical is attacking the triple bond and forming an intermediate product, which was also detected by gas chromatography. The intermediate product gives away electron to copper 28 and become the main product of the reaction. We compared defective copper 28 with non-defective version of it, and we also compared with copper chloride, which is used in this specific reaction. We found out that copper 28 has highest yield, and also there is no byproduct, which is homocoupling byproduct. However, in the copper 28, we observed a formation of homocoupling product, and this direction of research is still going on, and we want to understand why it is happening in copper 29, as well as we want to understand the effect of ligands. So this research is ongoing still. And to sum up, I would like to highlight that we characterized defective copper 28 and also non-defective version of it, which is copper 29, we stabilize them by available ligands, thiolate and phosphine ligands, and we perform their structural and optical characterization. We found out that defect on the surface of copper 28 plays a crucial role, causing a distortion, lowering symmetry, and also changing the packing mode. We found out that copper 28 acts as an effective photocatalyst for CC-Sonogashira reaction, and it has high selectivity and crucially suppresses the undesired homocoupling byproduct formation. Last part of my talk would be about nanocrystals. Now we move from nanoclusters to nanocrystals. As I said, nanocrystals has always size distribution, and we cannot crystallize them, and we cannot study them with single crystal XRD. However, we can use TEM to study their morphology, structure, structural details, and also growth mechanism. In this talk, I will be talking about indium arsenide nanoroll, indium antimonide quantum dots, and gadolinium oxosulfide nanoparticles. TM has a lot of advantages. First and foremost, it's a very high resolution. We can get to atomic scale. Also, we can work in different contrast mechanisms as bright field and dark field. We can do chemical analysis, also in situ experiments. However, one of the biggest advantages here in KAUST that we have 7 advanced TEM, which any of us can use, get trained and use. This is unique for KAUST, and I used this opportunity to learn TEM, and I mastered them, which opened up for me a lot of doors for different projects, which I would share with you. All these TEM pictures were taken by me, by the way, in this part of my talk. All right, now we move from nanoclusters to nanocrystals. Nanocrystal is wider field, and today we would be talking about specifically quantum dots. Quantum dots are semiconductor nanocrystals, where their optical properties are determined by their size. Quantum dots in visible range was studied a lot. And today I would be talking about quantum dots which absorb light in infrared region. They have a lot of promising applications: spectroscopy, surveillance, autonomy, food crop analysis, gas temperature sensing, and etc. I would like to bring your attention to this chart. If we look to materials which were used in this region, IR region, we see that mostly, if we bring our attention to the red one, the red materials were studied a lot because it was easier to synthesize them. But however, there is a problem. Problem is that all of them has heavy metal as well as they are toxic. In many countries now, you cannot use these materials in any optoelectronic devices. If we look to these 2 materials, they look very promising. They're covering all IR region. However, there is very less report on them because of course, the challenge of making them. Conventional methods use either very highly reactive precursors, which are toxic, which is pyrophoric, etc. And or they use strong reducing agents. In both cases, we don't have control over nucleation and growth, which limit the size of nanoparticles which we make. And as we can see, they had a limitation in absorption, which stopped in 1200. We didn't open all capacity of these materials, even for a fraction. Our approach was straightforward by using available precursors. And without going to details of the synthesis, I want to highlight the key point here was the complexation, which allow us to control nucleation and growth. We synthesized indium arsenide quantum dots in a very pure phase, which we confirmed. And we found out by TEM that these particles has anisotropic shape, and they are very crystalline. So the shape will come shortly. Let's talk about the size tunability, because as I said, quantum dots properties are determined by their size. So to be able to control the size is one of the fundamental tasks. So we were able to control the size of this nanorod from 15 to 33 nanometers, which gives us the absorption from 12 to 18. Now we are going deep into short wave infrared. And in this region, we have a lot of possible applications which we can use this material. Let's talk now about why it is forming as a nanorod. We stopped the reaction in different stages in order to find out how the mechanism of growth working, and we did TEM. In initial stage, we found out that there is only indium nanoparticles are forming, which are reacting with arsenic complex to form this shape. I want to highlight that by the reaction time when the indium nanoparticles are going to deplete, the particle is going shrinking to the smaller side and smaller, and at the end they are coming to the point when they are nanorod, when the indium nanoparticles are depleted fully, as we can see here. Another interesting thing, if you pay attention, there is a twinning on the surface of these nanoparticles, and this project also ongoing, and we need to do more HRTEM to finalize this project. Similarly, we synthesized indium antimonide colloidal quantum dots. It was pure phase. We could tune the size from 3 to 8 nanometers, which brings about an absorption similar to indium arsenide, which is from 1200 to 18. Again, it's opening a door of a short wave infrared region. Last nanoparticles that I will talk today is gadolinium oxosulfide, nanoplates. So this material has the advantage of high yield, and it's used in X-ray imaging. But today I will be focusing more on growth mechanism. So growth mechanism is kinetic here. By the time the size of the particle is growing, and we found out that by TM, we found out that by the time in the beginning, initially it's forming as a flower shape structure. Then it's becoming bigger and dissociating. And at the end, we are reaching to the hexagonal shape. I want to highlight here that the size dictates a performance, as I said. And here, especially when we have a bigger lateral size, we'll have bigger light yield, which is very important in X-ray imaging. But however, we observed that in all cases, the thickness of nanoplates are the same. That's why we call them nanoplates. And they were highly crystalline. Now, the next challenge was how to increase the thickness. And we were able to do it. And it's first time on these materials, someone can do a thickness control. By using seed growth method, we control the thickness. We double the thickness. And this doubling thickness even brought to the twice higher light yield, and which is, we can say, almost highest for nanoparticle of any material which was used in X-ray imaging. To sum up, I would like to highlight that we developed a novel synthesis, and we tuned the size of indium arsenide and indium antimonide quantum dots, and we characterize them. We conducted an examination of the growth mechanism on HRTEM. Also, this investigation in general enables us to control over the nucleation and growth, which gives us the possibility to fine-tune their properties and find promising applications. So finally, we come to the conclusion of my work. And this dissertation presented the explorative study of nanoparticles, including nanoclusters and nanocrystals, from two aspects. From fundamental, when we study the structural and optical properties of this material using their single crystal as a platform. And we understand the correlation, which is very important, of structure diversities with the optical and catalytical properties. For the practical aspect, we used the synthesized materials in different fields like catalysis, and indium arsenide and indium antimonide can be used in IR detectors. We didn't still make the device from it, and Gadox nanoparticles films for X-ray imaging. We come to the end of my talk, and this is my journey. I started my PhD in 2019. During my PhD, there was a COVID, and the first my project was about copper 15, and second copper 28 and copper 29. I was more focused in the beginning of my PhD on copper nanoclusters. When I mastered them, I got the opportunity of learning TM. When in our group we needed someone who can do TM, I jumped in, and this opened up for me a lot of projects, which is finished and going on still, including indium arsenide and indium antimonide and Gadox nanoparticles. As I mentioned, there are also, I didn't stop working on copper nanoclusters. Copper nanoclusters is also going on. We are trying to collaborate with our collaborator, Professor Magnus, to find out other applications for copper nanoclusters. Okay, finally, this is key publications. I would like to take this opportunity and thank my advisor, Professor Osman Bakr, firstly for giving me opportunity to work with in his lab. I have been doing also internship in this lab. I like the project very well, and I remember in the second day of my internship, I told Professor Osman that I want to join this group. However, he said that you should prove it. The fact that I'm here, I proved it. So thank you very much, Professor. You give me opportunity, also guide me through it. Thank you very much. I really appreciate all your advices and support. Also, I would like to extend my appreciation and thank to all committee members, Professor Omar, Professor Shadi, Professor Luigi, and Professor Irshad. Without you, this dissertation defense wouldn't be possible. I really appreciate your feedback, and thank you very much. I'm just lucky to be in the surrounding these brilliant people who teach me a lot and collaborate with me a lot. Thank you, guys. I really enjoy working with you, and it was my pleasure to become one of the friends of you. So thank you, guys, for all your support and for coming today here. So last but not least, I would like to thank all my friends, the KAUST, to giving me opportunity that I will never forget. So far, this is the best part of my period of my life. And also, I would like to take this opportunity and thank my wife, my son, who is sleeping there, by the way. So for their support, they are really the pillar of my strength. Thank you.
Thank you, Syed, for primarily staying within time. I would say the floor is open for questions from the audience. Do we have someone?
Maxim.
Still dynamic.
I have a more general question. What is the driving force to keep the exact number of copper in clusters?
Okay, very good question. So As I said, copper nanoclusters in general, they are similar to molecules, right? If you remember, I mentioned that there is a magic number, which means that we don't control all over it. We cannot say that I want to synthesize copper 61, let's say, and I will do the reaction in order to get that. How it works is opposite. We do reaction, recrystallize, and then we got to know what is this material. It works in different ways. But however, this is actually a challenge for scientific community to be able to synthesize what they want specifically with this magic number. Like let's say if it's copper 28, specifically I will target this number of atoms. In my case, when I used copper 28, copper 29, it's of course a lot of hard work, but also luck. We were lucky to get that one of them very similar structure with defect and non-defective version of it. Yeah, it's a good question. There is a here.
Okay, there we go.
Best of luck, Said, and thank you for the very nice presentation. So knowing that this year quantum that's got the Nobel Prize, what do you think will bring the Nobel Prize for the nanoclusters? And the second question, especially in the 21st century, most promising materials, they find their applications very fast. So what do you think is going to be the game-changing application for the nanoclusters, or why it's not very, still not widely used in the industry?
Very good question. Also to all society of scholars who work. Okay, the first question, I forgot. Okay, about Nobel Prize. Yeah, Nobel Prize. I forgot to mention quantum. This year, Nobel Prize was awarded to the scholars who work on quantum dots. However, still there is a vacancy in copper nanoclusters because they are different and they are playing a crucial role in the field. But still, we are lacking a bit of application part, which is not as wide as in quantum dots, because quantum dots is already used in, for example, this screen can be. However, copper nanoclusters, in general, nanoclusters are more fundamental, and still we are going there. As I showed that the graph that the research is growing exponentially. Hopefully, we will reach one day to the Nobel Prize as well. Copper nanocluster, yes, as I showed, like if we remember in the beginning of my PhD, we didn't have much copper nanoclusters. Yeah. Thank you.
Any more questions from the audience? Okay, doesn't seem to be the case. So I would ask you to kindly leave the room and leave some space for the committee to gather and